Hi everybody, I hope this video finds you well. In today's video, we're going to be finishing up the introduction into basic probability. To do that, we're going to sort of follow up from our last couple videos that introduce you guys to the basic definition of probability, some terminology like sample space and event, and also how to build a probability model. In this video, we're going to focus on introducing a couple basic probability rules, namely the complement rule and the addition rule. We're going to give one extra sort of definition between a relationship between two events called mutually exclusive, and then we're going to look at a couple examples. At the very end of this video, we'll also do one quick sort of tangent, which is that we'll take a look at how probability can sort of be related to statistical variables through a concept called discrete random variables, and we'll look at an example of that as well. So to start off with, though, we've got a couple basic probability rules that we'd like to discuss. The first one gets this fancy name called the complement rule, and what it says is that the probability that an event does not happen, so the probability of not E, is 1 minus the probability that it does happen. Now, there's not much to really say about this rule because even though it gets this fancy name, the complement rule, you guys already sort of know this rule. What this is sort of saying is if you know that there's a 20% chance that it is going to rain tomorrow, then the chance that it is not going to rain is 80%, because what you're doing is you're doing 1 or 100% minus the probability that it is going to rain, 20%, and that gives you the 80%. So this complement rule just says the probability that something does not happen is 1 minus the probability that it does happen. The second sort of major basic probability rule that we want to introduce is called the addition rule. So the addition rule is used when you have an or, and it sort of tells us the chance that we get one thing or another to happen. So the addition rule says the probability of E or F, so that event E or event F happens, is equal to P of E plus P of F minus P of E and F. Now, there's a couple things to keep in mind with this addition rule. First of all, when you see this or here, you have to understand that this or is the mathematical or. When you say the mathematical or, you mean this or both, right? When you talk about E or F from probability, like for example, if you said that you were going to go home and eat a pizza or eat a hot dog, well, then you would be telling the truth mathematically if you go home and you eat that pizza, or if you go home and you eat the hot dog, or if you go home and you eat the pizza and the hot dog. So, or here does not mean one or the other, it means one, the other, or both. So what this addition rule is saying is that the way we calculate the probability that one thing or another happens is we add the probabilities, but we subtract any overlap. And I want to show you guys just a quick visualization of why that sort of makes sense. So we're going to just do a little example down here. We're not going to do this as a probability, but just as sort of a counting exercise. So say we've got some different colored like numbers, right? So say we have like a blue 1, a blue 1, a blue 2, and a blue 2. And then say we have a sort of red 1, a red 1, and a red 2. And say we wanted to calculate like the probability that you get blue or a 1. So what this sort of rule is saying is that the way you would do this is you would look at the blues, so that would be all 4 of those, and you'd look at the 1s, which would be all 4 of those, but then you would take away the overlap. And that should make sense. If you go back and you think about taking all the blues and all the 1s, there's an overlap where these two blue 1s have been double counted. So the way we would calculate this, if we'd say, okay, all the blues, that would be, well, 4 out of 7. Plus, then we'd say, okay, all the 1s, there would be 4 out of 7. But then we'd have to make sure we don't double count and we take anything that is both blue and 1 out. And there would be 2 of those. So we'd subtract 2 out of 7 and we would call that 6 out of 7. Now, remember, these probability rules are sort of just rules. We should be able to get this same answer by just manually counting and being careful. Remember, our goal was blue or 1. So if we just count, that would be 1, 2, 3, 4, 5, and 6. Those are all the ones that are blue or a 1. And notice that that is 6 out of 7. So this addition rule just tells you that when you're doing an OR, you need to use addition, but you need to be careful about double counting. All right, one sort of very special definition that sort of goes hand in hand with this addition rule down here is what's called mutually exclusive. So two events E and F are said to be mutually exclusive if they cannot happen at the same time. So mathematically, two events E and F are mutually exclusive if the chance that E and F happen is 0. In other words, they cannot happen at the same time. Well, if you have two things that are mutually exclusive, then this addition rule becomes a little bit simpler, and we call this the special addition rule. So the special addition rule says that if E and F are mutually exclusive, then P of E or F is just P of E plus P of F. In other words, if the two events are mutually exclusive, there is no overlap, so you can just go ahead and directly add the probabilities. So this special addition rule only applies when things are mutually exclusive, and it says when things are mutually exclusive, then you can just simply add and you don't have to worry about any overlap. All right, we've got these couple new rules and this new idea of mutually exclusive. Let's take a look at some more examples of trying to use these rules and just getting more comfortable calculating probabilities. All right. So in this example, we are going to go back to sort of supposing we have a group of people in a room. So we have 9 people in a room. These people are Aaron, who is male, Andy, who's male, Annie, who is female, Bob, who is male, Carl, who is male, Cindy, who is female, Danielle, who is female, Donna, who is female, and Emma, who is female. And we're going to suppose you select one person at random. So we're just going to get comfortable calculating some of these probabilities. So the first one is we want to get the probability you get someone who is a female. So if we were to use our notation here, we would say the probability of a female is equal to, okay, well, we know it's going to be a fraction. It's going to be out of 9 because there are 9 people in the room. And now we just need to figure out how many would satisfy having a female here. So we have Annie, Cindy, Danielle, Donna, and Emma would all satisfy the sort of female property here. So we have 5 out of 9. So our answer here, sorry if that's a little messy, and sorry about the dog in the sort of background there. That would be 5 out of 9. So the probability that we would choose somebody at random from this room and they would be female is 5 out of 9. All right, let's try the next one. Notice we didn't need any probability rules there, right? That was just sort of directly easy to sort of calculate and count. All right, let's do the next one. We want the probability starts with C. So we want to get the probability that we choose someone whose name starts with C. So if we look back, right, there looks like there would be 2 people who would do this, right, for us. Both Carl and Cindy have names that start with C. So it would just be 2 out of 9. All right, next we want to get the probability that they are male and starts with A. Okay, so this, remember when you see and, that means that they have to have both of these traits. So we need to have them be male and we need to have their name start with A. So Aaron would satisfy that because he is male and has a name that starts with A. Andy would satisfy that because he is male and has a name that starts with A. Annie would not, because while she has a name that starts with A, she is not male. And people like Bob or Carl would not do it because while they are male, they don't have a name that starts with A. So this would just simply be 2 out of 9. And again, those 2 people would be Aaron and Andy that would satisfy that. All right, now we want to get the probability that you have somebody who is female and starts with B. So we need them to be female and have a name that starts with B. Well, there's only one person whose name starts with B. It's Bob, and he is not female. So this would be 0 out of 9, which is 0. What this tells us is that it is impossible to pick somebody out of this room who is both female and has a name that starts with B. So this tells us that female and starts with B are mutually exclusive, right? Just to use that sort of terminology from the last sort of definition we just gave, we could say that female and starting with the letter B are examples of mutually exclusive events in this room. There is no way you can select somebody who has both of those traits. All right, let's go ahead then and get to the next one. Right now we'll start having some ones that have an or in there. So we want to have the starts with B or starts with D. Okay, well, let's think about the ones who start with B. That would just be Bob there. So that would be 1 out of 9. And then the ones who start with D, that would be, looks like Danielle and Donna. So that would be 2 out of 9. And then we need to think, do we need to sort of be careful about any overlap? Was there anybody whose name started with B and started with D? Well, obviously starting with B and starting with D simultaneously is impossible. So we don't have to worry about any overlap. We just add those together and we get 3 out of 9. So there are 3 people in this room whose name starts with B or starts with D. All right, let's get to the next one then. Probability, now we want them to be female or starts with A. So let's go ahead and do that. First, we want them to be female. So that could be Annie. That could be Cindy, Danielle, Donna, or Emma. That's 5, right? We actually calculated that earlier, so 5 out of 9. Plus, starts with A, well, that would be Aaron, Andy, or Annie. So we plus 3 out of 9. Now, was there any overlap there? Was there anybody who was both female and started with A? Well, there was Annie, so we double counted her. So we need to subtract 1 out of 9, right? Because we double counted Annie, we counted her once when we counted all the females, Annie, Cindy, Danielle, Donna, and Emma. And then we counted her again when we did Aaron, Andy, and Annie as the people who started with A. So we need to remove her once, so she's only counted once. And then we should get here that this is equal to 7 over 9. All right, last one. Let's go ahead and get the probability. Name does not start with C. Well, we know that that can just be done as 1 minus the probability that the name starts with C, right? This right here is using that complement rule. We're just saying, well, we could try to think about everything that does not start with a C, but it might be easier to do 1 minus the chance that it does start with C. So that would be 1 minus. How many names start with C? Well, it just looks like Carl and Cindy. So it would be minus 2 out of 9. And then, of course, you can do some fraction work. Think about this as 9 over 9, and you should get 7 over 9. Of course, we could have also done this manually without this sort of complement rule by just saying, okay, which ones do not start with C? Well, there would be 1, 2, 3, then 4, 5, 6, 7, right? Just by skipping those ones that do start with C. All right, so this hopefully just gave you guys a little bit more practice calculating some probabilities, also made use of sort of the terminology we introduced, the mutually exclusive, and we also got to see an example of actually using the addition rule where we had to be careful with the overlap. We'll take a look at another example sort of similar to this on the next one. All right. To do this next example, though, we're going to give a quick definition about sort of a very common source of probability. We've talked a lot already about dice and cards and things like that. Dice and coins and stuff like that. Now it is time to talk about cards. So when we talk about a standard deck of cards in this class, we mean a standard deck that has 52 cards. These cards are made up of 4 suits: hearts, diamonds, spades, and clubs. You guys should keep in mind that spades and clubs in most decks are black and hearts and diamonds are red. So you will sometimes hear hearts and diamonds referenced as red suits and spades and clubs referenced as black suits. Every suit has 13 types of cards associated with it. So you have the number cards, 2 through 10, and we do call those the number cards. So these guys here are called number cards. Then you have Jack, Queen, King, and these 3 right here, these are called face cards because they have faces, right? The Jack, Queen, and King all have faces. And then you also have an ace. The ace is not a number card and it is not a face card. Remember, aces don't have faces. So what this gives you is you've got 13 types with 4 suits. That gives you 52 cards. In other words, there's sort of 1, 2 of hearts, then there's 1, 2 of diamonds, then there's 1, 2 of spades, 1, 2 of clubs, then there's 1, 3 of hearts, then there's 1, 3 of diamonds, 1, 3 of spades, and then 1, 3 of clubs, so on and so forth. So there is 1 of each of these types for every suit, which gives you 52 cards overall. We're going to calculate some probabilities here. Let's suppose you draw one card at random from a standard deck of cards. You want to calculate these probabilities. What's the probability that you get a heart? Well, let's go ahead and make sure we can calculate that. Yeah, we want that. Yep. Okay, so probability that we get a heart. Well, if we think about that, we know that it's going to be out of 52 because there are 52 cards in the deck. How many of them are hearts? Well, we know that there will be one heart for every one of the 13 types. So we can get this as 13 out of 52, which is a totally fine answer. Now, pretty much anytime we do probabilities, we just leave the fractions as their sort of most basic form. We don't bother simplifying. But do keep in mind, if you just sort of note, right, 13 out of 52 is equivalent to 1 out of 4. And notice both of these are sort of valid ways of thinking about this. This 13 out of 52 is saying that there are 13 hearts out of 52 cards. This 1 out of 4 is saying hearts is 1 out of 4 suits. So they're both the same number, but they sort of say the probability in different ways. All right, let's see about the probability that you get a 7. So the probability that you get a 7. Well, how many 7s are there? Well, there will be a 7 of hearts, there will be a 7 of diamonds, there will be a 7 of spades, and there will be a 7 of clubs. So that means the probability would be 4 out of 52. There are 4 7s out of 52 cards. If you simplified that, again, you don't need to, but just to help you guys sort of think about it, it would be 1 out of 13. So what is that saying? Well, 4 out of 52 is saying that there are 4 7s out of 52 cards. Or you could say that 7s are 1 out of the 13 types. So 1 out of the 13 types. Either way is valid for thinking about it. All right, what about getting a face card? So probability of a face card. Well, face card is not just one thing. That's really the probability that you get a jack or queen or king. Well, obviously you can't get a jack and a queen or a jack and a king or a queen or a king at the same time. So we just add these directly. For jacks, there would be 4 out of 52. For queens, there would be 4 out of 52. And for kings, there would be 4 out of 52. Because remember, for every type, there is 1 of each suit. Adding those together, we can say that there would be 12 out of 52 cards. Right? 12 out of 52, meaning that there are 12 face cards out of 52 cards overall. If you were to simplify this one, right, you could divide top and bottom by 4 there, and you get 3 out of 13, because that would be saying that these are 3 of the 13 types. But again, we can just leave our fractions sort of in their unsimplified form. All right, now we want to get the probability that you get a heart and face card. So what cards will be both a heart and a face card? Well, that would be the jack of hearts, so one of those, the queen of hearts, one of those, and the king of hearts. So there would only be 3 out of 52 cards that are both hearts and face cards. Remember, whenever you see that and, you need to think of things that have both of those traits. So they have to be a heart and they have to be a face card. All right, let's see then if we can get the probability that you get a heart or face card. Well, we know that this should be the probability of a heart plus the probability of a face card minus any overlap. So let's go ahead and do that. Probability of heart plus probability of face card minus probability of heart and face card. But notice we calculated all those, right? We calculated the probability of a heart right there. We calculated a face card right there. And we calculated the probability of the and right there. So this should just be 13 out of 52 plus 12 out of 52 minus 3 out of 52. Which if you calculate, sorry, it's a little messy there, looks like you should get 22 out of 52. So there are 22 cards in the deck that are either hearts or face cards. If you think about that, what that actually is that there's all 13 of the hearts and then all of the face cards that are not hearts. So the 13 hearts, then 3 face cards that are diamonds, 3 face cards that are spades, and 3 face cards that are clubs. That's 9 extra face cards on the 13 hearts. That's how we got to that 22 hearts or face cards. All right, let's go ahead and try the next one then, right? So let's see if we can get the probability that you get red and a number card. So we need the card to be both red and a number card. Well, the number cards, there's 1, 2, 3, 4, 5, 6, 7, 8, 9 number cards. And of course, we need it to also be red, so it could be hearts or diamonds. So that sounds like that's going to be 18 out of 52. Right? There will be a 2, and then a heart and diamond, a 3, heart and diamond, 4, heart and diamond, so on. And if you count that, you should get 18 out of 52. All right, let's try to do the OR then. Probability of red or number card. Well, we know that that's going to be the probability of red plus the probability of a number card minus the probability of red and number card. Notice we have to be careful, just like in this one back here, about that overlap, because we just found out that red and number card, there's ways for that to happen at the same time. So we do need to make sure we account for that overlap. So red, well, we haven't done that already, but red should be pretty easy. It's going to be half of the deck, right? So that is going to be 26 over 52. Plus the number cards, well, number cards, we said that there's 1, 2, 3, 4, 5, 6, 7, 8, 9 number cards and 4 suits. So 9 times 4 sounds like it's going to give us 36 out of 52. And then we need to subtract any overlap. Well, we just found the overlap is 18 out of 52. If we do that, 26 plus 36, that's going to be 62. Then minus 18, that sounds like 62 minus 18. Sounds like 44. So we should get 44 out of 52. Does that sound right? Yeah, that sounds absolutely right. 44 out of 52. All right. So we're saying there that the probability that you get a red or a number card is 44 out of 52. All right. Last one here, right? Your last pair here. Let's go ahead and get the probability that you get a number card or face card. Oh, sorry, and face card. Excuse me. So we'll just back up a little bit. And face card. All right, so we need to think what cards are number cards and face cards. Well, number cards are these guys, face cards are these guys, so there aren't any. So this would be 0 out of 52, which is 0. So we've just seen that number card, face card are mutually exclusive. If you bet somebody that you're going to get a card that is a number card and a face card, well, then you're pretty much out of luck because that is impossible. Those are mutually exclusive events. So when we go to do this guy, the probability of a number card or a face card, this will be very easy. Because we know that they are mutually exclusive, we just need to add these directly. Number cards, well, there's those 9, and with 4 suits, that's going to be 36 out of 52. Face cards, we've actually already done. We did it back up here. It's 12 out of 52. And if we do that, that's 48 out of 52. So the probability that you pull out a card and it is a number card or a face card is 48 out of 52. Does that 48 out of 52 make sense? Well, that sort of seems to indicate that there's 4 cards out there that are not number cards or face cards, and we actually know what those 4 cards are. Those are the 4 aces: the ace of hearts, the ace of diamonds, the ace of spades, and the ace of clubs. Those are the only 4 cards out there that are not number cards or face cards. All right, so this gives you guys a lot more practice with sort of this idea of working with and or, right? Remember, and means that they have to have both the characteristics, or means it could be one, the other, or both. Whenever you're working with or, you've got to be careful about making sure you eliminate any double counting. All right, we've got one last sort of example in this video here. We're going to talk just really briefly about how some of this probability stuff can apply to a more sort of data-driven side of things. Everything we've been doing so far has been sort of done more just from a purely conceptual side of things. We haven't really seen data or anything like that for a while. So we're going to just take a quick look at sort of a connection between these. So this is going to be a sort of a quick aside on a concept called discrete random variable, or what is sometimes called a discrete probability model. So to do this, we're just going to take a look at an example, right? What we're going to see is that we're going to see a probability model here, but for the sort of outcomes, The outcomes are going to be values of what we would normally see as a quantitative statistical variable. So in the example we're going to do is we're going to suppose you are studying the number of vehicles owned by a US family. So you get the following probability model. So we're saying that there's about a 19% chance that a family owns 0 vehicles, 29% chance that they own 1, 30% chance that they own 2, 15% chance that they own 3, and so on. So these are your outcomes, and these are your probabilities, just like a normal probability model. The only difference here is that the outcomes this time are actually values of a statistical variable, right? So each of these represents the number of vehicles, which is something we've discussed previously as sort of a quantitative variable. So we're going to do a couple things with this. We're going to confirm that it's a probability model. We're going to draw something called a probability histogram and describe the shape. It's going to be very similar to a normal histogram to the standard histogram that we've seen. Doesn't necessarily mean that it's going to be normally shaped, just like a standard histogram. Calculate mean and standard deviation, which is something we used to do a lot, but we haven't done for a little bit. And then we're going to calculate some probabilities here, right? So we'll do all this on the next page so we have a bit more room. So there's our information, right? The first thing we want to do is we want to confirm that this is a probability model. Now, this was just given to us in the problem, so how do we actually check that it is a probability model? There's 2 rules for probability models we discussed in the previous video. First one, we need to make sure all probabilities between 0 and 1. So let's just check that right quick. All those decimals, are they between 0 and 1? Absolutely. So we're all good. The second thing we need to check is all probabilities sum to 1, right? All the probabilities have to add up to 1. So we can do that. 0.19 plus 0.29 plus 0.30 plus 0.15 plus 0.04 plus 0.02 plus 0.01. Well, let's check that. 0.19 plus 0.29, that's 0.48. Plus 0.30, that's 0.78. Plus 0.15, that sounds like 0.93. Then 0.97, 0.99, and 1. So that adds up to 1, and there we go. So this thing that was written down for us really is a probability model because all the probabilities are between 0 and 1, and the probabilities actually sum up to 1. All right, let's see if we can draw this thing that's called a probability histogram. So let's think back to how we drew sort of our old school histograms. Well, old school histograms, you've got to draw yourself a little quadrant there. Remember that you normally would put frequency here. Well, we don't have frequencies, but we do have probabilities. And probabilities do the exact same thing. They measure how likely or how frequent these different values should happen. So we're going to label this side as the probability. And then we're going to put the variable down here. All right, so let's look at how we're going to sort of fill in these axes. For the probabilities, right, we can see that we had a low probability of 0.01 and a high of 0.30. So we might go like by 0.05. So there's 0.05, 0.10, 0.15, 0.20, 0.25, and 0.30. So there's 0.05, 0.10, 0.15, 0.20, 0.25, and 0.30. If you really dislike working with decimals, you could of course change all of these into percentages and then write these as percentages as well. For the variable, well, what we're going to do is a little bit different. We're actually going to sort of give ourselves some equally sort of spaced marks here for each of these. Now let's see how many we're going to need. We're going to need 1, 2, 3, 4. It looks like we have 1, 2, 3, 4, 5, 6, 7 things. So we'll need sort of 7 spaces for columns. What do I have already? 1, 2, 3, 4, 5. So a couple more, like 7. But instead of labeling at these marks like we normally would, we're going to label the middle of each of these. So this first one is going to be for 0, then 1, 2, 3, 4, 5, and 6. So notice that the big difference here, because all of these are just discrete values, single values, they're not ranges of values like we would have for a normal histogram. We're labeling these in the middle of each section. So not at those hash marks, but actually in between. All right, now we just draw bars to the appropriate heights. So the first one should be at 0.19. So that looks like something like that. Then the next one is at 0.29. Keep in mind, just like always, this is a histogram, so the bars should touch. Then 0.30, so just slightly higher. Then 0.15. Then 0.04. then 0.02, and then 0.01. And again, if you wanted to, you could fill those in. This is 0.19, this is 0.29, 0.30, 0.15, 0.04, 0.02, and 0.01. What sort of shape would we see here? Well, this seems to be the sort of middle, right? There's no room out to this side for a tail. Looks like a bit of a tail this way. So we'd probably call the shape here approximately right skewed. All right, so that is a probability histogram. If you guys are asked to build a probability histogram, just keep in mind the probabilities take the spot of the frequencies, and then when you label your variable, just make sure you label the middle of each one rather than the actual ends. And of course, we should probably also put the name of the variable here, number of vehicles. All right, now we're going to calculate the mean and standard deviation. To do this, we know that we're going to be wanting to use our calculator, but we have these sort of frequencies based on these values, so we're going to have to do a little bit of a trick here, right? What we're going to sort of do is we're going to put this information here in L1, so our variable in L1, and we're going to put the probabilities in L2. And then you're going to use your 1 var stat, and you're going to do L1 comma L2. Where this right here is going to be your frequency list. So you will use this if you have the slightly older calculator, or if you have the slightly newer calculator, right? All you want to do is you just want to make sure your frequency list is L2 here, right? So older calculator, just manually type in 1 var stat L1 comma L2. Newer calculator, just set your frequency list when you do 1 var stat to L2. When you do that and you actually run that 1 var stat, you will get the mean, and you should get 1.66, and that would of course be in vehicles. So the average is 1.66 vehicles per family. And for standard deviation, you guys will notice something interesting. If you've done this correctly with the frequency list, there won't be a sample standard deviation. Because if you think about this, these probabilities represent the entire population of information that we have. So we're going to have to use the population standard deviation. It's the only standard deviation that we'll be able to see. And in this case, you should get 1.26 vehicles per family. So there we go. So to calculate mean and standard deviation of a discrete probability model, just make sure you put the variable in L1, put the probabilities in L2, and then make sure you turn on that frequency list. Do keep in mind that if you have the slightly newer calculator and you actually were able to have a little spot that says frequency list and you put in L2, after you finish doing this problem, make sure to clear out that L2 from the frequency list so that your calculator will not use it in the future. This is, again, one of those rare instances where you want to use the frequency list. All right, let's calculate a couple probabilities here. For D, we want to get the probability they have less than average. Well, what was the average? Well, so that means it's less than 1.66. Well, how would you have less than 1.66? That means you would either have 0 or 1. So this is going to be the probability of 0 or 1. And how do we get those probabilities? Well, we just look them up here, right? There's no overlap because you can't have 0 and 1 at the same time. So we just add these up, 0.19 plus 0.29, and that is going to be 0.48. So that tells us that about 48% of people have less than the average number of vehicles, because we calculated the average as 1.66, and the only way to have less than 1.66 is to have 0 or 1. All right, let's do part E here, probability at least 1 vehicle. Well, at least 1 means that you could have 1, 2, 3, 4, 5, or 6 vehicles. Now, obviously, you can go ahead and just do this manually by adding up the probability for 1, 2, 3, 4, 5, and 6. But we can do this a little bit more cleverly by using the complement rule. We can do 1 minus the probability of any way for this not to happen. So what are the ways that this cannot happen? Well, there's only one way. You have 0 vehicles. So we do 1 minus the probability of 0 vehicles, which is going to be equal to 1 minus the probability of 0 vehicles is 0.19, and that should give us 0.81. If you actually just go through and manually add these up, well, 0.29 and 0.30 is 0.59, plus 0.15 should be 0.74, then 0.78, then 0.8, then 0.81, and that gives us the same answer. This is just a nice little sort of trick using the complement rule to make things go a little bit faster. This wraps up our introduction into probability. In the next set of videos, we're going to be talking about some more advanced probability calculations, specifically starting off with what are called conditional probabilities. Those will be probabilities with extra information.